this computer. Hello. Good, sir. Great. So thank you all for coming again. I know a lot of us are on Zoom now. We have some people in class, which is always nice. So let me share my screen. Where are we? So we are in our pages, rockefelleruniversity.github.io. Hello, sir. And as always, we're working through our courses in order. If you want to come across our videos, they are still here. I am keeping up to date, I think.
Welcome to the YouTube channel.
So I just added the first sessions for Bioconductor this morning. It takes a long time to upload some of these. But we should be there if you want to catch up on anything. Let me hide this panel. And we have introduced ourselves to R. We learned a bit about plotting. We learned about the types of data we're going to handle, how we can visualize this in a linear genome browser. And then we started looking at how we can handle the different types of biological data which we are going to come across. Just organize myself a little bit. Tracks fit data to window. So what did we do so far? We introduced ourselves to Bioconductor. Most importantly, hopefully we saw how to install a Bioconductor package. We looked at how we can handle FASTA files effectively, or genome sequence data, which is important because we're going to need this to align. Any of you doing things like phylogeny will also be working with FASTA files, so it's important to know. And then we introduced this concept of genomic intervals, which is effectively just a way of storing ranges with additional information attached to it. The important thing here is this allows us to do very simple things like overlap one set of ranges with another, and we can see what was actually overlapping or not overlapping, and then we can use that for further analysis. So very simple things like do my ChIP-seq peaks overlap with my transcriptional start sites? We can do that just using GRanges. So next thing we're going to cover today is kind of the next level of complexity with genomics data. And we're going to start to look at genomic scores. So this lecture is quite short. I think we should be done way before 1:30, but I'm going to try and take my time. Okay. And if you have any questions, throw them in the chat. I think we have David here back. Maybe not quite. Oh, maybe it's off the side of my screen. Nope, but I'm sure he'll be turning up. But if you have any questions, unmute yourself and ask, or just put them in the chat. So genomic scores. So genomic scores is a very generic statement term. Because we have genomic intervals, I think we have genomic scores. And genomic scores are just that. They are the same as a genomic interval, but we have some value attached to each interval. And the way genomic scores are kind of held classically was using this wiggle format, which I hope you guys never have to see because it's awful to create. But effectively, you have this line here which tells you I am variable step. The rest of the file doesn't seem to be, but it means that these gaps could be variable. It's on chromosome 21, and here they actually say the span is 5. So we have from this position on chromosome 21 a score of 50, this position to this position a score of 40, this position to this position a score of 60. So there's a way of having, along the linear genome on a particular chromosome, the value at that position. Often it's binned to save space. Right, so again, from here to here, we have a value of 50. From here to here, we have a value of 40. Much more compressed, human-readable version of this format is bed graph, which again are very easy to make, and they are effectively a bed 4, whereas bed 3, chromosome, start, end, Here we have chromosome start end, and then we have score associated with that particular window range. But you can see really clearly and why this saves so much space. These are all can be all the variable ranges, and then here, when we have no scores at all, we don't need to write out every 5 bases that it's 0. We just write from here to the end of the genome, it's 0. So that's how we can store values in beg graphs. And if you were to create this, this file is valid just to read into IGV, and you can start to review it. It's valid to work with other programs that import it. Usually, though, we're not going to be dealing with beg graphs, because even with this level of compression, there are times where you sequence deeply or you just have signal at all points across the genome. This compression isn't really helping you much. So in order to have a format which is both compressed and allows us to randomly access, jump in and out of particular regions, we can use bigWig. So this is a wiggle file, but for whatever reason, a big wiggle file. So hopefully we saw that in our last session. In the exercises, we had to download a bigWig, and we looked over our peaks to make sure that we had signal. And already you can kind of see the difference between things like beg graphs, where we have this lack of information. We've summarized to say this region we have a peak. In a bigWig, we can see a lot more, right? We can see the center of the peak, and we can see the distribution of signal around there. And perhaps we could even tell, wait, why isn't that a peak? It looks peaky to me. Okay. So genomic scores are used heavily in genomics. They are, as we've seen, they are typically the first. This is a bigWig here, so it's a genomic score. It's the first thing you look at when you get your data. I don't think I've loaded in. Look this way rather than that way. But here I can just review my data. I can see my signal over my exons. Over my exons. And, you know, as we saw, you can zoom in and out really quickly with bigWigs, right? That's full chromosome coverage. It's not stuttering, and this is because we have this dynamic indexing, and we can take advantage of that both in IGB, but I'll show you how we can save memory and just read in bits of the bigWig we need in R. So they're used for things like RNA-seq, ChIP-seq, ATAC-seq, probably most important in things like ChIP-seq and ATAC-seq, where you really do spend a lot of time looking at your data. But things like phylogenetic conservation, how conserved is this gene, which parts of it are conserved well, we can see signal over the gene. Things like GC content of the genome, all these are held as bigwigs. So in our session, genomic intervals in Bioconductor, we reviewed some of this data from Mick. I'm not sure if it was actually this one. I think I might have chosen the wrong one. So and on this page, this is the great thing about ENCODE. If you go to file details, they have the raw FASTQ, and I think we went and downloaded some of the bed files. We can also see we have bigwigs of the actual p-value. I guess they calculated some signal p-value, which is probably based on this, where they have the actual test sample, the IP, over an input control sample. So we can get bigwigs if we want to review them and start to play with them from places like ENCODE, which just allows us to get them and start with. If you haven't downloaded it already, download it here. If you want to follow along with the exercises, it is actually quite quick to download, but sometimes it takes a bit of time. So I think in the last session, as I said, we looked at Mick. We looked over this locus, gamma beta 2 locus, and we compared the signal here with that where we could. So I provide the bed graph and bigwigs for today's today's exercise, but I have filtered this down just to a little region because the bed graph could be huge, and I want it to be part of the package of the course. We also have the bigwig here. So to work with genomic scores, we don't need to know any more packages. We can use just our track layer. Remember, our track layer is our IO tool for genomics data. It allows us to import most formats. And Genomic Ranges is going to allow us to handle interval data. Remembering that this is effectively interval data with a score. So we already know the tools we can or we need to be able to get this data and to start to manipulate it. We should have already installed our track layer, so we can just import the library our track layer, and this is going to allow us to load in both bigGraph and bigWig. We'll also be making some uses of some functions from Genomic Ranges, but note, we don't actually need to load Genomic Ranges directly. So if I was to Google our track layer, and go to its page, got a build error, that's bad. But somewhere here it says depends, so these are the lists of packages. It imports, depends, suggests, effectively just means that all these tools will be loaded when we load our track layer. So we're going to get Genomic Ranges for free, and we did this library our track layer. It needs to load Genomic Ranges to work. First function we can look at is import bigGraph. So let me get my session oriented. So I want to be in the right working directory, set working directory, choose directory. Downloads. I think I downloaded Intro to Bioconductor last time we were here. Go, our course. So the first function we could look at is we had import bed from the GRanges packages before, from the rtrack layer packages before, sorry. So we can use import.bedgraph. And this should just do something very similar to import.bed. Look. Bedgraph. We can see we do get something very similar to what we were getting with the GRanges before. I've probably got it on my slide here. So just looking at the first three, we have our chromosomes, we have our ranges, we have our strand, and then we have the score for that particular range. So this first part here, where we went from 1 to 728,000, we don't have any scores. Okay, so this is a nice example of it saving a lot of space. I think it's worth noting here that bigGraph don't have any strand information. So bigGraph and bigWig are both strandless. So that's kind of frustrating. So if you have stranded RNA-seq and it's meant to be on one strand over the other, we don't get that information in bigGraphs and we don't get it in bigWigs. So if you look here, you can see you have the star, but we do have the ranges we're interested in, and we have the actual score over that particular. So from this position to this position, I have that score, that much signal from the bigWig or big. Again, GRanges always have plus, minus, star as their levels. There's nothing to stop us actually going and correcting the strand information. The issue is when we, inside R, we can't import or export bigGraphs with strand information. So even if we changed it and tried to export it later on, it's going to set it back to star. Most of the time, you're not going to be working with bigGraphs. I don't think there's an option for a bigGraph to be downloaded from ENCODE. Most of data is stored as bigWig, and I think we've talked about this a little bit before. There is alternative formats for this. There are things like TDF, tiled data format, which is built into IGV. The fact is UCSC created the bigWig format, and it has become the most popular format storing this genomic scores data. To handle it, we can just use the import.bigBW function, and that should just import our bigWig into exactly the same format as the bigGraph. Okay, we still have the seq names, the ranges, no strand information, and we have the scores. Okay, so there's no difference in the actual content we import it from biggraph or bigWig, they both contain the same information. It's just the bigWig will be hundreds of times, if not thousands of times smaller. So far, we've retrieved these genomic scores as biggraphs and bigwigs as GRanges objects. Okay, so we know GRanges objects, hopefully. We covered them briefly in our last session, and we're going to see a lot more of them as we go along. That means that once we've got this file in this format, once we've imported it like this, we can use all the same GRanges accessors, overlaps, nearest to that we previously used. So here I'm just going to create a GRanges chromosome 1 from here to here, and then I can use the standard overlapping functionality of GRanges to find the ranges in the bigWig I just imported, which overlap with these GRanges. Okay. Once I have that, I can actually do this. Maybe we should just do this in R quickly. My R has got smaller and smaller. Okay. So then we've imported that. We have our GRanges. If I just want to do some overlap test, I can create another GRanges very easily. Yeah. So this is my GRange here. And if I just want to pull out the ranges in the bigWig, which overlap this range, I can do my bigWig over my other GRanges, and that will give me a true false, the length of the bigWig file, so 2161, telling me whether or not a range did overlap one in that short GRanges I created. So we can see there's a whole section here which overlapped. If I actually want to subset down to them, I can do my standard indexing using this logical. I can just pull out the ranges of interest to me, those which overlap that particular. Yeah. But most of the time, I believe, and you obviously have the ability to work with GRanges any way you want, but most of the time, I think when you're working with genomic scores, you actually want to keep them as something more like an RLE. So we're going to change this function import.bw. We're going to point to the same bigWig, but now we're going to change as, we're going to change that to an RLE list. So if we look in the actual function import bigWig, not what I wanted. So import.bw. Should see that it gives us some options here. Oh, here it is. Object, the object to explore. It's either going to be an RLE list, an integer list, a numeric list, or something coercible to a GRanges. By default, it's going to import them as a GRanges. The only other format we're really going to deal with is this RLE list. Okay, and this is run length encoding. We have seen this. I've just pointed to it briefly in classes before, but we haven't really discussed it. So when we import this bigWig, it's not going to import it just as an RLE object. It's actually going to import an RLE list, and you will have an RLE object for every single chromosome. It's the same as, say, when we had a DNA string, we needed to turn it into a DNA string set, where we had a DNA string representing the sequence on every chromosome. So we're going to import this, import.bw, set the as to be RLE list, and then we can say class here just to check what we got back. And it says simple RLE list from that package iRanges, which is obviously the package we use to set ranges. So we have, I'm sure you've seen RLE encoding in some way before. And really it's just a way of us efficiently storing long stretches of repeated values. So when we were looking at what makes up a BAM file, we saw that we had this part of the actual SAM, so the human readable version, this thing here. This is a really simple version of run length encoding, right? Rather than saying M 100 times, it tells us we have a run of 100 M's, right? And that just saves us a lot more space. There's only 4 characters there effectively versus 100 M's. And then we can have slightly more complex ones we saw in our BAM files before, SAM files, where we had, say, 28 matches in a row, 1 deletion versus the reference, and then 72 matches. Okay, so already we've seen RLE in some way. We actually saw it also in our last session. We just didn't comment on it because we don't really need to mess with it yet. But when we got the GRanges, we actually saw that the seq names for these files were stored as a factor RLE. Okay, and then we had again values, we have lengths. So we have this chromosome 1, 891 of them in a row. And then we have chromosome 10, 737 of them in a row, etc., etc., etc. Okay, so maybe if we just go look at the GRanges, we can see here GRanges, seq names, and it tells us the name of the object at the top. It's an RLE. This is an iRanges. The strand was also an RLE. Just to save space. We've got 152 stars in a row. It just saves space to save 152 stars. Okay, so for genomic scores, we're going to be storing these long stretches of numbers in the RLE. And to store genomic scores across chromosomes, we're going to have an RLE list. So every chromosome will be an RLE. Encoded in it will be all the scores across the whole chromosome, and we'll have one of them for each chromosome in our list. To create an RLE is really straightforward. We can actually just use a standard vector of numbers. So here I've got my numbers, and I'm just going to create a stretch of numbers with 5 zeros in a row, 3 ones, and then the rest of them zeros. If I want to convert that to the iRanges version of an RLE, I'll just do RLE and pass in my numeric. And you can see it does that. Okay, it doesn't need to be whole numbers, it can be decimals as well. From that, we can then easily construct our RLE list. So we can go and then maybe create another vector. We still already have our numbers here. And we can just do RLE on our first numbers, RLE on our second numbers. And that's going to create our 2 RLE lists, sorry, 2 RLE objects. And then if I want to give them some context, like chromosome they're on, I can do RLE list. And this is just like a standard list creator function, where we will do chromosome 1, that's the name of the element in the list. We give it the scores, the RLE object. Do another name for this element, and then give it the RLE object. And then we have our RLE list of length 2, and each element named chromosome 1, and then chromosome 2. So RLE, as I keep saying, allows us to compress space needed to store genomic scores. And we'll see a lot of RLE and RLE lists inside Bioconductor objects. We can actually see, if we look now at our bigWig we've read in, and we just look at the first 2 elements, which will be here, the first 2 chromosomes, we can see it saved a lot of space already. We have this long stretch of zeros encoded there before we actually had some data in our file. This ... it doesn't want to show us the whole thing. And it goes to the end of the file where we have a lot of zeros here as well. But then the whole of chromosome 10, I can just do in 2 values. Let's have the length, and that's all 0. To access these these RLE lists we've read in, so remember this, my bigWig here was imported from the bigWig straight as an RLE list. So now if we want to start to access information within that RLE list, we can just use our standard list accessors. So most objects will allow us to access the elements within them using these types of accessors. So we can do $ and then just put the name of the chromosome we're interested in, or we can do the double square brackets, and pull out the actual chromosome name. Okay, so now I've got no longer an RLE list, I've just got a numeric RLE, I've got an RLE object, which contains the scores across the chromosome. How have I got? So now, even though this does look like a really strange object, what's nice is we can interact with it largely like a normal vector. So we can save all this space, but we can still index it, for instance, like a normal vector. So if we have this long RLE object, and I want to get just the first 10 values, the first 10 base pairs of my chromosome, I want to know what the values are over them, I can just do standard square brackets, and then 1 to 10. And it's not going to return me back a vector, but under the hood, it's going to do that little bit of indexing and then return me back again a numeric RLE, but this time just of length 10, right, what I've indexed it down to. So I've imported it here. I can subset down to the chromosome, and then I can do standard indexing to retrieve that region. I can also alter my RLE, right? So if I've imported a bigWig, and now I want to normalize it, maybe times it by a particular control value, a number, I can do that too. So I can do here, I'm going to replace some values. I'm going to go first 10. I will now set them to be 100. And if I look at it, you can see it's altered my RLE. Now I have 10 where it's 100. I have less here where it's then 0, and then back to the normal data. Okay. So RLEs, they look weird here, but I can index them like normal vectors, and I can index them and replace like normal vectors too. Okay, the work's being done under the hood somewhere in that package. If for whatever reason I don't want them to be an RLE anymore, which you really might not want them to be, we can do as vector, and we can, here I'm indexing just to take out the first 10 values, and I'm back to a standard normal numeric vector. More usefully, perhaps, if we can remember that ggplot likes data frames, if we want to extract values from a bigWig and then pass this to ggplot to plot, we're going to want to turn it into a data frame, and we can do that very easily with just as.dataframe straight on the RLE object, and now it's going to give us the value, what was at that, and the actual position as the row name. So that's really handy, and we're going to do that in the exercise. Get a bigWig, basically make your own kind of IGV plot over a region. When I first discovered RLEs, what got me really excited is that we can also do arithmetic operations, mathematical operations, logical operations, and get some summary statistics from this. So we can do things like plus 100 to a numeric RLE, or we can do more complex things with BODMAS, brackets, operations, whatever. So here I'll just add 100 to everything. If I want to add 100 and then times by a scaling factor, I can do that too, plus 100 times by 10. And if you're operating in R, what's really nice is that this is very fast and memory efficient. And it's not like it's not that long. It's quite a long vector here, that many values. But under the hood, R will do this at great speed for us. Another great thing we can do with RLE operations is logical operations. So RLE object is logical operations. So in this case, if I have my numeric vector, sorry, my RLE vector, and I want to know which positions across that chromosome were less than 10 reads or 10 signal, I can also do that in one line. I can just say curl whatever underscore RLE less than 10, and now you can see it's turned my place where I actually had scores here into now trues or falses. Right? So I've gone from a numeric RLE into a logical one. Okay. But under the hood, it still just acts like a standard logical vector. because I can then use that with our indexing we just saw earlier on. I can use my logical operation here, and I can set anything which is, say, less than 10 to be 0. Okay? I might decide that it's not worth having values less than 10, they're too small anyway. So I'm going to set a ceiling and I will make them all 0. That will save me space in my RLE as well. So I can do that just in one line, take that numeric RLE, find out which is less than 10. This gives me a logical. I can use that to index the original RLE and set everything which was less than 10 to be 0. We can also apply summary functions, summary statistics to our data, and there are a number of them. I haven't listed them all there. We can go look in a second. But we can do things like mean, and very efficiently, it's going to find the mean of that whole RLE list. We can do max, and we can do things like sum on our RLE. We'll go get the sum of the whole numeric length, the max, or mean. Very, very usefully, we don't need to actually just operate on the RLE object itself. We can apply these operations to the RLE list, which we've imported straight from bigWig. So in this case, if I do import the bw and I give it the bigWig, I tell that to come in as an RLE list. Now, if I do my bigWig plus 10, we can see it's going to apply this to every chromosome. Right? We don't need to worry about looping through every chromosome, applying this and putting it back into the object. Under the hood, it's going to do this for us. And if I do plus 10, you can see here, bigger values, and it's added 10 to every other chromosome too. The same goes then for summary statistics. So if I want to get maybe the max for every chromosome, I can then also pass that in as here as max, give it my RLE list object, and I can just look at the first ones and it's telling me the max on chromosome 1 was this, but we know the other chromosomes weren't. So I think the really nice thing here is that once you get these things in as RLEs, as you can imagine, this is for chromosome 1, but you could select the region you're interested in, and then you could apply your normalizations, remove them, maybe turn them into a data frame, and then start to visualize it inside ggplot2. I have to use GRanges then to also index our RLE list objects. So the GRanges will provide the intervals from which genomic scores are retrieved, and the resulting RLE objects contains an entry with the score for each interval in the GRanges object. So let's actually try and put this in action. We will create a GRanges here. We'll import the MIC chipseq file. So these are the peaks of calling MIC in CH12 versus its input. I'm going to resize these and then 50 fixed on the center, and then we'll find the MIC peaks which overlap just this region on chromosome 1. So now we should have a bigWig, which I believe was MIC signal. And now we have some MIC peaks where we would expect to see some significance. So if we look at them, we have chromosome 1, and they should be all the same size. They should be 50 base pairs long, maybe 49 here, 50 base pairs. And we have the score, which was the score from max over these regions. To get the actual signal over these peaks is super easy using GRanges and RLE lists. So if I have my RLE list, which is imported straight from that import.bw function, we can see that I can just use standard square brackets here. Don't need to worry about double square brackets. I can just pass in my my GRanges I've just created, which is these two here. And now I have an RLE list. The naming is not particularly sensible. It's just taking the name from here. Maybe if I assigned a name to it, it might work. But we have across that 50 base pairs, the width of the peak, we have the actual signal for every base pair across it. So I've managed to kind of rejig our bigWig we imported here. We have these lengths for every chromosome. And now I can index that bigWig by the GRanges, and now I get an hourly list, the same length as my GRanges I'm using for indexing. And I have the scores across those peaks. I can then start to use our summary statistics functions like sum. And I can get an idea how much overall signal was in those peaks by using the bigwigs. So this is now a real nice feature of these summary statistics. Is I've given a bigwig and I want to get some information from some particular regions in a GRanges format. I can extract all the signal across them, and then I can use summary statistics to start to give some type of overview of it. Okay, we've only got a few slides left, actually, so we'll do more. We may wish to export our RLE list or RLE objects back to a bigwig file. So once we've done all this alteration, once we've done our normalizations, so we've maybe read in a bigwig, we've times it by a value, we've set everything below 10 to be 0, whatever we chose to do, we might want to then export that again. Okay. If we're working with an RLE object, we need to turn that into an RLE list object before we can export it to a bigwig. And it was the same with DNA string and DNA string sets. When we had a DNA string, we needed to put it into a DNA string set with a name so that when we wrote it to a FASTA, we have that FASTA header with the name and then the sequence underneath it. But we need to do the same here because we're going to create an RLE list and every element will have a name. And that will be how we know the differences between the RLE objects. And that's how things like IGB will look for chromosome 1 in the name before it starts to load it. So as simple as that, we just need to recreate our RLE list. We're going to say chromosome 1, we'll give it the RLE object. Now we have our RLE list of length 1, so we only have one chromosome there. So that's good enough, then I can export that using export.bw. And then that will create for us a valid bigwig, which we can then use in IGV, or we can pass to other people to import into R or import into other people. In some cases, we will only wish to import portions of a bigwig file. So in reality, if you're working on your bigwig on your laptop, there's no reason to read in the whole bigwig. You've got all that information, which maybe you're not interested in. So if you really are working in peaks, perhaps you're just interested in looking at the peak regions. Okay. So this is a really useful trick, which will save us memory and time. I've been getting better the internals of this system, but importing a bigwig bigger than 2 gigabytes will be 16 gigabytes on your laptop. So we want to save some memory here. We don't want to install load in the whole bigwig. So we can do this with, there's lots of tricks in Bioconductor to just import the bits you need. And for this one, we can actually pass an additional parameter to import.bigwig using the selection parameter. Okay. We're also going to need a new function, bigwig selection. And this is actually going to create a selection object, which we will pass to the selection parameter inside the import.bigwig function. Okay, so importing only a portion of a bigwig, we simply just need to specify again the GRanges of regions we wish to retrieve to this bigwig selection function. So if I just want to get regions over my peaks, I will just pass it a GRanges of my peaks. So we already have my new MIC peaks. We already created this earlier on. So we have these 50 base pair windows. If I just want to import data over that, all I need to do is create a bigwig selection object by using the bigwig selection function. giving it a GRanges, and then that creates this bigWig selection object. Having created that, I can then do import.bw, give it the path to the bigWig. Again, I'm going to tell it it's an RLE list. But in this case, I'm actually going to say, just look at this region. And what it does is it imports our RLE list, but it doesn't change the coordinates here. I still have all these zeros. It just means I will only get scores over the regions where that GRanges is. So if you're sure that you just need to look at these regions, this is going to save you so much memory, so much time. So it can be very slow. All right, so that was quite a quick session. Maybe before we go, I just want to give some slightly out of. So if you are interested in bigwigs, we talk a little bit outside of R for a sec, because I want to be kind of practical. Another really good tool for working with bigwigs is deep tools. And what's really great about this is the guy who wrote deep tools, or one of the authors, actually writes some of the internals for bigwig import. So it's a guy called Devon Rowe. What's really useful about that is that they are kind of comparable. You can use similar tricks in both. But I do recommend, if you wanted to do bigwigs outside of R, you can do them in deep tools, and that will make your life easy if you don't want to get comfortable with R. So it's this one, I think, bigwig. He actually wrote R-lib-bigwig. That said, deep tools will show you how to use that from inside R later on in our session. So I think I'm going to cover that in some later sessions when we start to do visualization. In fact, you can see a little bit of it here. We have a separate course for it if you're interested, and that shows you how to install deep tools and some of our other tools, but I think we cover it here as well, working with deep tools. I think the R way is perfect. It works really well for me, but I know a lot of people do use deep tools, so I want to point. Great, so we think we have some exercises at this point. These are a little trickier. I'll give you a little bit of time. Scores. I really can't get that thing to work from the exercise link at the top. But let me just open up the slides, and I'll come back at just before 2:30 to run through the solutions. I will record it as well, and then we can get on with our next section, which is, oh, I've skipped ahead to our next section, which is looking at genomics, genomic features, which is actually GTFs, gene models, and what we will use to do counting in our next, when we start to do RNA sequencing. So I'm going to stop the share for now. I'll pause the recording and we'll pick it up just before 2:30. If anyone wants to head off recording. So I'm just going to run through the solutions quickly, or we'll just look at the solutions. So we're working with genomic scores, working with bigwigs. I'm not sure if this is still true for anyone working on Windows. Let me know. I think now Windows supports the bigwig libraries. Download the signal p-value bigwig file for replicate 1 for this experiment. So direct link, we could have downloaded it there, or I think I had it open earlier on. Signal p-value, and then it has the replicate. So we could probably order it like that. Either this one, did I say replicate 1? Yeah. Okay. So you could have downloaded that. Load our track layer, we load genomic ranges. Again, I'm doing it here again. So what are we going to do? Read the bigwig signal for this particular region, okay, as an RLE list. So we can create a GRanges for this region. Here I've put down GRanges, seq names chromosome 1, and I've just specified the ranges as an iRanges from there to there. I think we could also just do it the very simple, easy way as well. I'm not sure why I don't. Remember, we can actually create GRanges directly from that kind of setup, where it's chromosome, colon, position, start, position, end. So we could have done that rather than create it so explicitly here. But we need that GRanges so that when we import the signal, we can set the selection. So we're going to use those GRanges, pass it to the bigWig selection function, and then that will give us a bigWig selection object. And then I can use import bigWig. I specify the bigWig. I need to say as already list. But importantly, by saying selection, I'm only going to read in data from what would be a full-size bigWig file just over the region of interest. And hopefully you would have seen that really didn't take up much memory, took barely any time. Reading the whole bigWig in and then filtering down to the region of interest would have taken way more memory and a lot more time. Find the maximum and minimum value of bigWig signal in this region. So I guess here, I don't think I've done the min here actually, but we did max, chromosome 1, and then I can specify indexing this particular region. Actually, I don't need to because I've just read in data only from that region. So I could just do max of that chromosome. So this is the thing I was saying in class. It's kind of nice that we're going to show you ways of making these plots using a program called GViz, but you can do it yourself in ggplot too. So producing an area plot. So I just wanted to give you the hint that we need to use geom area. Of the signal over the transcriptional start site plus or minus 500 base pairs of the gene start for this gene. So I guess you would go look at that gene and then we could define where the start and the end is. So here I'm going to do a sequence of numbers from this position, which is the start or the TSS, minus 500. And I'll do this position plus 500. We could have done a GRanges and then used the resize function to do that too. That would have been cool. Here I'm just doing it very simply. Once I have this sequence, let's just have a look what that actually looks like. It should just be a string of numbers. Okay. I'm then going to use that to index my RLE list, my RLE object. I look at chromosome 1, and then I can use square brackets to index to pull out signal from chromosome 1 over this region. Okay. I then turn it into a data frame, which means it's now ready for ggplot2. I'm going to add additionally another column called position, because I want the position to be shown along the Y, the actual genomic position, rather than just 1 to whatever. Now I have a data frame. I can do library ggplot. TSSDF, so I'm passing it our data frame. I'm telling it Y should be the value. X will be the position, so that's what I produced here. Remember, when I turn this into a data frame, the score column gets called value. And then basic, that would have created my plot, but then I wanted a nice background, so I said theme minimal. I wanted the X lab to say genome rather than position, so I add my own X lab. I want the Y lab to say score rather than value, mine and ring. And then I'm going to do some tricks here, which is always useful. I'm going to do the theme, which allows me to change the angle of these across the bottom. I think that's a good example. I got to admit, I wouldn't remember to do that, how to do that. I would always Google this. There's an answer somewhere there. You can just see. But that looks a little prettier. Apply a log2 transformation to the genomic scores and save as a new variable. Okay, so I'm just going to save it as a new variable up front, and then I'm going to log to it and save it again. Okay, and this is another arithmetic operation we can apply to RLE lists. I think if we did question mark RLE, maybe somewhere here, it might give us a description. Oh, no. Maybe RLE list. Yeah. So it gives you an idea of some of the methods available here. And what we need examples of actually what we can do. One of these is log2. So we can just apply log2 to our whole RLE list. And then that gave us the value here. If I want to export that again, I just use the export function from our track layer, export.bigwig, give it the thoroughly list we want to export, and then we can give it the name of the file we want to create. And it's log2.bigwig. I think, as I remember right, I'm not sure if anyone got to this part in the exercises. Let me know. But I remember. Not minimize this when I'm recording this meeting. I remember that there is a problem with displaying this in IGB. Right? So if you had a problem, actually all you needed to do was right-click the axis and say reset data range. And it was just to do with when we do a log2 of 0, it breaks, right? So in this case, I think this is the problem here. Read in this data file, and this is a peak file, but remember this is the max version of this peak file. So if we actually read it in, we can have a quick look. It claims to be an XLS. I think I've said this in class, but it's not. So we don't need to use RIO, the special package for importing Excel files. We can actually just use read delim. And it turns out it's tab separated, and this is the trick people do. If you create a tab separated file and call it .xls, Excel just wants to open it, it's associated to it, and as it opens it, it realizes it's tab separated. So you will never know. We also need the comment char, because if we look at these files, it's annoying, but they have, or it's a good thing, I think. They have, oh, this might be quite a big file. Oops. Geez. Okay, sorry, let me, I'm having, sorry about that. If you have issues on this exercise, just put it in the chat and I can come back to it at the end when we do the exercises for the second session. Thank you, sir. Okay, so we have mic peaks. We deliberately avoid any comment characters because in the max chip output, sorry, they tend to put like the information on how the peak calling was done at the very top of their pretend Excel files. So there you go. So if you look here, we can see all this information with a tab. We don't want to read that in. We just want to read the information from here. So this is why we do this comment char is hash. And then we have a standard file, data frame now, but we really have information we can put straight into a GRanges, right? Chromosome start end, and then maybe some scores. So that's what we'll do. We'll build our GRanges from that data frame, take the chromosome column, take the start and the end, give that to an iRanges function. So it makes the iRanges we need. And then additionally, I will add 2 more columns, which are going to be metadata columns, fold enrichment, and -log10 pvap. Now I can use the standard GRanges actions. Oh, actually, I don't need to here. I'm just going to go down to those on chromosome 1. So I will take the seq names from our GRanges. I will just find which ones are chromosome 1 using in, and then I'll subset our GRanges down. Use the GRanges as a mix port, mic peaks, import in the mic chip-seq bigWig signal over the peaks on chromosome 1. Again, we're just going to create a bigWig selection based on these GRanges. And then once we have that bigWig selection, we can just do import.bw, supply the bigWig, supply the bigWig selection object we just created, and tell it it's an RV list. Import the GRanges gene positions. We're going to deal with gene positions properly in our next session. But in this case, I've just created a file of gene positions, start, end, ignoring exons. Filter to genes on chromosome 1, identify peaks overlapping the gene's promoter, here defined as a region ranging 2000 upstream to the transcriptional start site. So we're going to go from the TSS where the gene starts, 2000 base pairs, and assuming that's the promoter region. And we're going to split our peaks up into those which overlap this region and those which don't. So we'll read in the peaks as a data frame. We'll make a GRanges like we did before out of the various elements we need. Chromosome name, start, end. I'm going to add strand because genes, obviously, it's important to have strand. And then I'll add some IDs as well. So I'll set the names for my GRanges this way. I'm then going to resize these. And first off, I'm going to resize them to be one base pair right at the start. And then I can then resize them using standard kind of method again. I'm saying now I'm going to set width 2000 and it's going to go from the end. Right? So if I said from the start, it would go into the gene. As I say from the end, it's going to go away from the gene. With that now, I can then overlap my GRanges with those over the promoters. If I want to do the opposite, I'm going to do the GRanges over the promoter positions. But if you look carefully, I've got an exclamation mark here, which reverses the logical. So true becomes false, false becomes true. Okay, create a violin plot of sum of bigWig signal within peaks at promoters and those without promoters using ggplot. So we have our bigWig peaks. I'm gonna have a look what that is. So bigWig peaks is the reads, is a signal overall peaks imported up here. So this is our RLE list. I can then do what we did at the end of our session, where I'm going to create now a new RLE list, and each element will have the signal across that peak taken out from this bigWig data here. And then I can get the sum. Right, so this is going to go across all those elements and give me the sum of every peak. So that's going to give me, I say peak maxes, it should say peak sums. I'm going to do the same for the non-promoter peaks. So again, I have just a vector here of peak sums. And then I'm going to create a data frame from these because we're going to use ggplot. It always wants data frames. And I have one column called peak max promoter, which will be the sum of the signal over these peaks. And I will add to this a column saying promoter or not. I'm going to So I don't need to, when I'm making a data frame, I don't need to have a vector the same length as this. If I just say promoter here, it's going to do promoter over and over and over and over. So I'm going to create another data frame for the non-promoter. I will just row bind these together using rbind. Finally, I can then pass this to ggplot. And I'm going to do X. I will use this newly created column, promoter or not. Y, I will use the sum, which is the sum from here over these peaks. And then I'll do G on violin, great. And then I'll do scale Y log 10. So I'll use the scale functions to correct the scale for me. And then we're going to do a bit of scale fill brewer here. I'm going to use a certain scale just to make it look like this. Okay. Export of bed file of TSS peaks whose sum of chipseed signal is twofold greater than the median of all peaks sum signal. Okay. So first off, we'll get the median of all peaks we have. Right. So we already calculated this, but I'm going to calculate it again. The sum over these bigWig list objects. I'm going to concatenate them together for both the promoter peaks and the non-promoter peaks, and I will take the median. I will then look at promoter peaks where this what I calculated earlier on, this peak somewhere up here, peak promoter max. Here we go. I'm going to use that, and I'm just going to filter down to those where it was greater than the median times by 2. Finally, I will filter this down. I will export.bed, and I'll write this filtered peaks out to filterpeaks.bed here. So I'm going to create a bed file of these promoter peaks where the signal was greater than twice the median. Okay. That's actually kind of a complex exercise. If you have any questions, you can put it in the chat and I will try and answer it probably at the end of the session. Great. So the next thing we're going to cover is, again, super useful. It's genomic features in Bioconductor. This is really how we deal with gene annotation. So this is essential for RNA-seq, essential for ATAC-seq, ChIP-seq. So the first part of this, we'll look at the gene models. The first part we'll look at that. Second part, we're going to look at how you can just use the Bioconductor annotations to add, say, gene names to your Entrez ID. The Entrez IDs are really useful, they're very well regulated, but number one, Entrez ID isn't as useful as knowing it's alpha globulins. Okay. So we saw genomic features stored as GTF or GFF files before. And they look like this. You have a little bit like a bed file. You have chromosome start end. I'm not going to really go into details there. Start end. We have strand. I believe we have score in one of these things here. 2 more columns hold information. We have the source often in the second column. So in this case, they found it by blast. Often it will say unknown, or it may say just NCBI, whoever created it. Usefully, the third column tells you the type of feature this is. The exon, CDS, 5' UTR, stop codon, transcript, gene. These can all be descriptions we might have here. Strand. Really usefully, it has this, which is a tying together that this exon belongs to this gene. So it's often a feature, and we call this a meta feature. Right. So actually, if I got, say, all the signal over these exons, I might want to add that signal together to give me the signal for a gene. It's not quite that simple as we'll see because exons overlap, right? But this is how we tie features to meta feature, exons to genes, transcripts to genes. So we often find models as GFF, GTF. This importantly, as I just said, associates exons to transcripts, transcripts to genes, exons to genes. With this mapping, we can perform complex operations such as summarizing genome-wide RNA-seq signal to genes, transcripts expression. So these GTFs, this objects we're going to find or use today, we can use directly to get RNA-seq counts or quantify transcript abundance. Now, we also use GFFs and GTFs in IGV. So IGV, if we open it here, and I go to a genome we know, new session, let's say I select a lot of genomes here. HG38, you can see at the bottom I have this track. I zoom in, we have gene models. Expand this. We have multiple transcripts for one gene here, and we can see that we have, let's say, one transcript has an exon, and then a bigger exon here, and an exon there maybe, and we have direction by the arrow. And we know that all these exons together form a transcript, and all these transcripts together form this gene. So IGV takes a GTF or GFF and can build that display. GTF, I mean, there is this idea of a GFF and a GTF. They're very similar formats. In fact, GFF2 is GTF format. Bioconductor doesn't really matter. It'll import them both and parse them for you. So GTF probably is the most common format for gene models. In this example, and this is the minimal example I could kind of create. I did this by not quite hand, but pretty much by hand. For a gene, and this gene only has one transcript, and you can actually find this GTF just here in your data directory. And it has all this information we were talking about. As chromosome 1 has the source is unknown, it's actually because I created it. And then we have the types, we have exon, stop codon, CDS, so actual coding regions, and then the start codon. Actually, notice it doesn't have 3' UTR or 5' UTR here. It's because it's going to calculate it. When we do IGV, it will work it out by looking at the CDS and the exon, finding the regions where they don't overlap. They will be untranslated regions. It's just like start and stop codons as well. And then we have over here, and this actually is one column with the values separated by colon. So it's this column here. And in that column, we have things like gene ID, gene name, transcript ID, and TSS ID. So we know the transcripts it relates to, and we know the gene it relates to. So that's really what we need to be able to tie these things together. IGV, with that file, it'll be able to parse it into something like this. Where it puts the direction based on the strand, it has exons, and it's hard to see, and I should have made a bigger example. Sorry. But if you look here, at the end of this little bit here, maybe it's better on your screen, you can see you have a slightly smaller block here for the exon, and that's the untranslated region. Right. So probably the additional bit from, which way was it going? It's going that way. So the stop codon, there's probably a little overhang here. Yeah. But there's a region which is exon, but not coding. In Bioconductor, as I said, it does it really well. We have all these transcript databases pre-built for us. So most model organisms, certainly human, mouse, rat, software. As you can see here, there's plenty of them. They are all packaged into these TxDb packages with the naming scheme TxDb, species, so HD19, source, usually UCSC, major version, HD19, HD38, and then table, which was the known gene table. So I think we looked at this, but just to remind everyone again, we go to UCSC, oh, did it again, UCSC table browser, there's life outside genomics. So in the table browser at UCSC, already we can see this is HD19, UCSC genes, and we have a table here called known gene. So what's happened is programmatically Bioconductor have gone, basically what we would do is just download it from here. They've programmatically gone and grabbed that known gene table. Okay. We can, however, and this is really important, make use of GTFs and GFFs of our own gene models outside of Bioconductor. So this genomic features package allows us to import GTF, GFF, create this TxDb object, and then use all the functionality with that TxDb object, which is important, both because these objects are great. They allow us to really work low level with the gene models, but also we don't want to be stuck with just Bioconductor's annotation. Your lab may have annotation it believes is better, especially for non-model organisms. So this way you can really take advantage of all the functionality within the Bioconductor world without having to use their TxDb. But to start with, we will use their TxDb. So the first thing we'll do is have to install it. Again, if we need to get a package, we can just Google the name of the package and go to the page. It has this installation thing here. We would just copy that, paste that into R, press enter, and that would download and install the package for us. And once we have the package, we can just load the library, just like we were doing with the BS genome package. We just load this library with library. And then straight away, just like when we loaded BS genome H sapiens, it had an object available for us. Once we've loaded this library, an object is put in the environment called TxDb H sapiens UCSC H19. So the same name as the library, we get an object. You can see this object is a TxDb, and it comes from the genomic features package. Just like with a BS genome object, when we just pressed enter, we type the object name in, we press enter. It has a special display method where it shows us information on the TxDb. Here we can see supporting package TxDb genomic features, HD19, Homo sapiens, the taxonomy, the table it's extracted it from, the website it went to, the IDs in use, and then various other information, some of it just off the screen. Yeah. So just as they suggest, these TxDb objects are databases. They are a database object. So they're not just a data frame. We can't just extract information from that. In order to access these TxDBs, we're going to use special accessors. Luckily, these accessors are going to return data in formats we should already understand, GRanges and GRanges lists. So we have to learn some new accessors, but once we get the information, we can just use our standard GRanges on it. So the really important accessors are, which we've known the last one from our last exercise, our genes, transcripts, exons, CDS, and promoters. And they do just like they say, extract the gene positions, the transcript positions, the exon positions, the coding locations, or the promoters from our TxDB object as a GRanges. So I've just got some examples as we go through. We can extract the genes using genes. So I just do the genes function, provide the TxDB object. Gives me a little warning here, and this is just a feature of the annotation wasn't great back for HT19. So it's saying that there are exons for one gene on both strands, which is impossible, I think, unless there's some novel thing. So we can override that if we wanted to. I wouldn't recommend it. It actually gives you what you would need to do. But what we have back are seq names, our chromosomes, our positions of the gene, the full length of the gene, so all the way from the TSS to the TTS. Doesn't care about exons here. It gives us the strand. It gives us the gene ID. This is an Entrez gene ID. This is what I was saying. It's kind of useless. Entrez gene IDs are great because we don't have to worry about things getting translated in Excel. Sep1 will get changed to September 1 in your Excel, all this stuff. But I think if I search 1, what's that going to give? But I think this is hemoglobin or something. Sorry, alpha glycoprotein. Okay, so we can learn a little bit later on how we can get some more interesting or useful gene names here. But this is the information we get back by just running genes. We get the position of the gene, the strand, and the actual name of the gene. If we do exons, we're going to get all the exons, and this exon ID isn't so useful. It just numbers it 1 to the whole, to the last exon. So that's not too useful, but we have exon information. We have strand here. We can do transcripts. Now we get a transcript ID, again, 1 till the end. But usefully, we get a transcript name. This is all the same. We're just changing the name of the function. But we're getting a lot more. Now we're looking at exons and then a bit less for transcripts. And we can do CDS and we'll get all the coding regions. Usefully, we can also actually control what comes down in these metadata columns. So right now, we've had no control of what was in these columns. Remember, this is our actual GRanges here. And we have 2 metadata columns, TXID, TXName. Here we had exon ID, and here we had gene ID. We can actually control what's passed back to us by specifying an additional parameter here, columns, and that's going to control what comes out in these metadata columns. So often, if I'm wanting to get transcripts, I actually want to know what gene was associated to that transcript. Right, that makes sense. So here, I'm going to do columns, and I'll ask for both the gene ID and the TX ID. Probably be better to get the TX name. TX ID. I say we can look at this question mark transcripts, and that should give us an idea what columns are available. So again, every time we're confused about what we can do with a function, we should be able to do this. Oh wait, we've got to load genomic features first. You can see some of the columns here already. TXID. There we go. And it says here, columns must be null or character vector as given by the columns method. It's going to tell us some of the columns we can use. If I go down a bit, it actually gives us some examples as well in columns we can use here. So we don't just have to accept the default. We can ask for things like gene ID or TxID. You could have used CDS ID, or maybe TX name would have been sensible to control what comes back in these metadata columns. A function which we really could have benefited from in our last exercise was the promoters function. So in order to get a promoter, I think what we ended up doing is kind of getting the TSS, making that one base pair, and then going upstream 2000 base pairs. So it was a two-step function. Here we can just use the promoters function. We just give it the TxDb object. And we tell it how much upstream from the beginning of a gene we want to go and how much downstream. Typically a promoter would be a little bit into the gene as well. And then we'll get the promoters here by transcript. And we get the positions here. Two transcripts for one gene. They share the same promoter. So as we said at the beginning, it's important, and a major feature of this is that we can control, or we can associate features like exons to meta features like genes. So we have functions to extract data from our TxDb object, which will keep that relationship. And those are the transcripts by, exons by, and CDS by functions. So these are going to extract lists of GRanges. It's actually an object called GRanges list, containing the grouping of features to meta features. So we're going to have all the transcripts associated to a gene, all the exons associated to the transcript. We'll have a list. And each element will be a transcript name, and within there may be all the exons which belong to that transcript. So the transcript by function takes a TxDb object and a by argument specifying the meta feature to group by. So we'll do the first one here. Transcripts by, I'll give it the TxDb object, and I will say by gene. If I just look at the first two elements now, we can see that we have a GRanges list. So it's no longer GRanges. This is named by the name of the gene. Right? So by gene, this one is 1, which we just looked up is something alpha glycoprotein or whatever. And then these are the two transcripts which can make up that gene. You can just see coming off the end of the page, we have next gene is 10. And that's only got one range, so there's only one transcript for that. This is just another way we can get back the information, but now it's grouped by the gene. And within each group, we have the transcripts in this case. We could have exons or whatever. As with all lists, none of these new lists like DNA string sets, RLE lists, or now GRanges lists, they can all be accessed and operated on like lists. They're just extensions of this. So we can use the $ and the double square bracket successors here. And this will extract the grouped intervals as GRanges. So if I want to get gene 1, here I'm just indexing 1. I've done $1, but I'll take my object I created here, and I will just subset to that first one. And now I have a GRanges of the transcripts for that gene. Similarly, we can do exons by, and we'll do exons by, say here, transcript. Now, for every transcript, I have the GRanges which make up, the exons. So here we have the first exon, here we have the second exon, here we have the third exon, and they're all associated now, not by gene, but by transcript. Naming's not great because it's still called 1, 2, and that's because we're actually using this transcript ID, which is the term. Okay, so then I was saying that, TxDb objects are great because really all we're going to do next for RNA-seq counting is get exons by gene, and we will pass that to our counting algorithm. That's going to be great. But not all TxDBs exist for every species, and you may have a different gene model which you want to take advantage of. So we can actually create our own TxDb objects super easily just by using this make TxDb from GFF. Okay, and it says from GFF, it's going to work with GTF. So it's going to look at the file, probably the extension, and know to import it slightly differently than some of the other formats. Okay, so we can do make TxDb from GFF. We give it our GTF. It goes, does this import, prepares the metadata, makes the object, and then we get an object which is the same class and from the same package as if we had downloaded it from the Bioconductor pre-built ones. We then type it in. It's not going to have as much information because we haven't had the chance to specify this, but it does tell me the data source, right? It was the one we just pointed to. I haven't given it any information on organism, mere base ID, genome. It does tell me how many transcripts it has, just one, which is still disappointing, but we have our TxDb object we can now work with. With that, we can use all the same features we did for their pre-built TxDBs, and now if I want to extract genes, I can do that. If I want to extract exons by genes, I can also do that, and I will get my grouped GRanges list. You can, and I don't recommend this actually. I don't know why I included this, but I don't recommend this. You can also directly import, create a TxDB from UCSC. So to do that, we're actually going to use some of the functionality within our track layer. So our track layer is our IO package, but it is also the package for interacting with UCSC. So they have a function called UCSC genomes. Maybe we can just run that because it doesn't look very good on this page. If we look, it will be a table of all the genomes we can, all the genomes which are available within UCSC database. How big is that? 280. There's lots and lots of different versions. There'll be multiple versions of the RAC human database because there are major versions, major updates. Okay, so once we've done that, we know what genomes are available to us. We actually then just go back to the function and we go make TxDB from UCSC, and we just specify a genome which we had seen in that list, in that table. It then goes and does some of the hard work. It goes to those UCSC. It selects the known gene table, but it looks for this genome, and then it will create a TxDB object for us. Okay. Question is and obviously then we can use all the functionality again within genomic features. I think the question there really is, why would you do that? Because obviously they're already pre-built for us. Perhaps UCSC is updated enough that it has a genome which isn't in Bioconductor. Remember, Bioconductor is 6 months releases, so it could just be late. But really, the problem I have with this method is that there is no intermediate, right? You don't have a GTF on your computer. You've gone straight, lifted this from that URL. And if that URL, for whatever reason, was broken on that day, or someone had made a mistake their side, you've already created the object. I think it's nice to have that GTF. Save that on your computer. Then you have some record of, this was the file which actually created my TxDB object. Once you've created your GFF or GTF, and often I will go and import a GTF, I will remove genes of a particular class, maybe from a particular list, and then maybe I will export them again so I can look at them in IGV or give them to a collaborator. We can actually just use this export GFF function from the R track layer object, R track layer package. Just give it the TxDB we want to export here. We can give it the connection we want to write to, and then we have to specify the format. Even though it says export.gff, we can specify the format as GFF, or I recommend GTF. So I've got some more useful functions, I think, here for working with genomic features, the last being really useful. So we've seen we can extract transcripts and exons grouped by the genes or transcripts using this transcripts by or exons by. So we can get all the exons associated to genes, and we can group the exons by the gene they're associated to. So here we have transcripts by genes, and then we can do the length, and it tells us we have 20,000 genes within this database. But it tells me nothing about how long each of the elements is. Right? So at this point, I have I've created an object like this, and I'm just seeing how many separate elements we have. This would be one element, this would be another. A really useful function, and it's not just particular to genomic features, but is the lengths function. So up until this point, we've used a length function. But if I want to know very quickly how long are the elements in each one of my lists, I can use the lengths function, and that will tell me how many entries I have in every element across my GRanges list. It will also work for lists. So if you have lists full of vectors, you can use lengths, and it's a lot quicker than looping through and getting the length or doing lapply and getting the length of every element. So here it's telling me the first gene has 15 exons. The transcripts, I've done exons by gene, called it transcript by gene. And then for gene 10, I have 3 exons. For gene 100, I have 12. For gene 1000, I have 16. For gene 10,000, I have 16 exons. Function which you want a lot for normalization is transcript lengths. So transcripts are made up of exons, and in order to get the real length of a transcript, we have to sum all the exons which make up that transcript. It's not good enough that we just look at the start of the transcript and the end of the transcript. There's splicing in many genomes, so that's not really the length. It's the transcript length. It's just the exon components put together. That again can take a long time to do in a loop. Loop through, you have to get the sum of all the exons. Here we can just use transcript lengths on our TxDb object, and it returns a data frame with our transcript ID, our transcript name, the gene ID, the number of exons, which is useful again, but then the actual length of that particular transcript. And I can tell you this is input for many other programs which want to do normalization or want to account for biases which arise from longer or shorter genes. We don't need to worry about having to pull it out from somewhere else. We can pull it out in one line from our TxDb object. A super useful function, and a function which again shows the interaction across these packages, is this extract transcript seek. Okay, so this allows us to kind of mix our BS genome with our TxDb objects. The BS genome holds the whole genome sequence. The TxDb object holds the whole gene models. We can do extract transcript seek to extract the sequence of the transcripts from the genome. So this accepts a BS genome object of the genomic sequence of interest and a TxDb object. So I'll load BS genome because we haven't loaded that yet. And I'll load the one for the appropriate genome. And then I'll get extract transcript sequences. And I'll give it the BS genome object to get the sequence from. I will provide to the transcripts argument the actual TxDb object we're working with. And then again, very quickly, it gives us back something we've already seen, a DNA string set. But now we have a one of length 82,000 because each one of these is the sequence for the actual transcript it represents. So this is great if you want to do transcript alignment, which we're going to come to later. If you want to do transcript quantification, the input isn't the genome FASTA, it's this. It's great because all those tools are written. A lot of those tools are written in R, so it's nice that we can really take advantage of the BS genome and the TxDb packages to get us the actual input to align to. Oh, and then with that, we know already if we want to write out a FASTA file, we can just do write x string set. We give it our DNA string set here. We just need to make sure it had names and it's inherited these names from the TxDb object. And then we just give it the file we want to write to. Here we're going to say my transcript sequences.far. That's our FASTA file we would use in the input for things like Salmon and Callisto quantification tools. Something which is going to confuses me a lot, it's a real pain, is that there are different chromosome naming conventions. So the big ones are Ensemble and UCSC. Ensemble does 1, 2, 3, 4. UCSC does cur1, cur2, cur3. That's a simple fix, you would think. It's not, because there's also things like mitochondrial chromosomes. I think it's cur-M and it's MT, so you can't just paste on cur. And then you get the random chromosomes, which are named very different. So converting this, you could just do this paste and you could replace the mitochondria and you could try and change the names yourself. But actually, I really like this addition from Bioconductor, which is the Genome Info DB package and the Genome Info DB data package. And what these have internally is the mapping from UCSC chromosome names to Ensemble. And they have the functionality to update our GRanges objects in a valid way. So they're going to change that really annoying factor levels we saw for chromosomes, seq names. It's going to fix that for us. So to take advantage of this, first we need to load the library. We can review what organisms are supported. Clearly they can't support everything, but there are a number of supported organisms, including human, Drosophila, mouse. So to get that, we just need to run this function genome styles. We'll get a list of all the mappings, and we can just see the names here. These mappings available to us. If we actually go into the list and we look at what is contained, say here, for the Homo sapiens human genome, we can see it really is kind of just a data frame containing those mappings, and it's telling us whether or not chromosome circular, so that's important for things like mitochondria. I can't remember the auto, what that means, whether it's a sex chromosome, and then importantly, for these major databases, dbSNP is a really important one if we're going to do SNP annotation. But then they're all on one, and all your stuff has chromosome 1 or whatever. But you can see here they're subtly different, CH1, CUR1, and there's this map which the Genome Info DB package is going to be able to use. So to do this, we can use this seq level style function. First, we can just extract some genes. So we have some genes in a particular style. And it'll be more fun to actually see this on the process. I don't actually have that available to me. HD19, so old, I don't have it on my computer anymore. Okay, we have our that kind of naming convention. If we load this library InfoDB, and I think it was seq levels, level style, and I can just provide it a GRanges. It's going to look at the chromosome naming and all the chromosomes available to it, and it will tell me what style it is. I say this is in UCSC style. Okay. If I want to change that to a different style, it's super easy. I just need to now assign, whereas if I ran seq level style with my GRanges before, it just gave me the style. I can actually assign it a new style. So here I'll do Ensemble. But I could have chosen any of these ones, MTBI, UCSC, dbSNP, Ensemble. And it will go and change all that for me. So you can see that in action again. Oops, sorry. Let's do So if we look at that now, it will change. So I did dbSNP here rather than sample, but you can see it's on Cur-19. And most importantly, it's clever enough that it's gone in and fixed all our levels for us as well. That's the real pain, as we know, changing factor levels can be a bit of a pain. Here it just does it all for you. It saves me so much time, that package. I really like it. So I think we're going to finish this just by looking at some more general annotation. So whereas the TxDb packages hold the gene models, some of the oldest packages in Bioconductor are the org.db packages, or org. Because these contain information on a gene's mapping to alternative IDs. If you've done any genomics, you just know that there are hundreds of IDs, hundreds of competing IDs for things like the human genome. Even like rarer genomes, Drosophila. If you go for mosquito, Leslie Bossel has her type of IDs. Vector-based has different IDs. Getting this mapping is important. So this gene annotation is contained within these org.db packages, and for every species you will have a setup or species available, which will be org, and then the species, and then the ID type. Typically this will be org.hs, and then the ID type is Entree's gene. It's the one which Bioconductor has chosen as their gene, as the one ID central to their mapping. Some genomes don't have Entree's IDs assigned, so they will have a different value. To access this annotation, as always, we need to install it. So we Google org.hs.eg.db. It will tell us how to install it. Once it's installed, we can load it, and we can do the class, and we can see we have an org.db class from the annotation DBI package. So whereas TxDBs were built by Genomic Features, annotation DBI builds our org.db packages. As with TxDB packages, we will need to use special accessors. It can't just be a data frame anymore. We need to be able to use accessors to get the information out of it. And we're going to use particular functions. Columns, this displays what kind of annotation is available. Key types, this tells us what type of identifiers can be used with this select function we will use. Keys, it tells us all the keys in the database. So in this case, all the Entree's IDs. And it's the select function which we can use with this org.db and our supplied keys. And when we say keys here, we mean IDs. What it uses to try and start the mapping. And also specify the key types, and we can specify what columns we want to get. So we're going to have a little go at this now. If I apply columns to my org.hseg.db object, you can tell it gives me back all the information which is available within this package. So we have Entree's ID, we also have ensemble ID, we have gene name, which isn't the same as symbol. Symbol's that short one, gene name is the full name, alpha globulin or whatever. But you can also see it contains functional annotation too. So we have some Go gene ontology information. We have some PubMed IDs, which you could use for literature searching. PFAM, protein database. I thought I saw path here somewhere before, but maybe, oh yeah, path, which would be KEGG, pathways. OMIM, which is the online mammalian inheritance in man or something. But it's effectively a disease database, SNPs which cause diseases. Mendelian inheritance in man. If you want to know more about the identifier types, you can do help, and then you can do the gene name. So help acunum, help gene name will actually tell you a little bit about this. We can also say, whereas this is what we can retrieve from the database, we can also look at what we can search for in the database. And this is the key types. These are all the ones available to us. And we're going to most of the time be using Entree's ID and trying to look up some sensible either gene ontology information or symbol. And if we do keys on a database, and here we say we want key type symbol, it's just going to give us alphabetically here, I think, or maybe not. I think this is ordered by the entrees ID number. It's going to give us all the symbols available within this database. So sometimes it's useful just to get all these symbols, which I can get. Here I'm just showing the first 10. So really what we want to do is use this now together to try and convert our keys into something more useful to us. So here, I'm going to take our org.hs.egd package. I will pass that to the select function. I'm going to specify the keys I'm going to use. So these are the values I'm going to look up in my database. I'm going to specify the key type. I'm going to say it's symbol. I know it's symbol, but I would make sure that the key type is in here. Right? It needs to be one of these available key types. I want to get back the symbol, the gene name, and the chromosome. Right? And these again need to be available within these columns here. Well, the chromosome's not available there anymore. But then this will give you back a data frame in the order of the keys you gave it with the information from the columns you asked for. I think this chromosome is actually being removed because they want it to be in the TxDb package, so it makes much more sense for it to be. So I think if you did this line, it actually gives you a warning. Chromosome being removed to the TxDb package. But here we can turn a key, a symbol, what we may have on the end of our GRanges, the names, into a data frame containing, in the same order, additional information as specified by the columns. So now we can actually have a go at this. Let's do the genes. We'll get the gene locations. And if we look, we can see we have our gene IDs both here, but we also have the names here. And if we want to then try and convert them, we just need to take those keys, and I'm going to extract all the IDs by doing gene locations $gene ID. So that will extract it from this column here. I will then pass those keys to, again, the org.hs.db object. I know that the key type is entrees ID. And then I can say columns, I want to get back symbol, gene name, and entrees ID. Yeah, it didn't give it back in the order I wanted, but it gave me entrees ID, the symbol, and the gene name. Okay. So this is a nice, easy way of just getting some sensible naming annotation for these kind of entrees IDs. That's the end of our sessions for today. We have some exercises as always. Again, these are going to start to mix, I think hopefully start to mix a few of our different lessons. I will run through the solutions for this at 4:30, but I think if it's okay, I will do it on Zoom. But I will hang around a little now if you have any questions. And anyone online who missed some of the solutions earlier on or wants me to run through them, just let me know, because I think I wasn't sharing my screen. So I'm going to pause for now, and then we'll pick this up at 4:30, where I'll just run through these last few exercises.